Hello everybody, and welcome to page 12 of the workbook. And in this video we're going to start talking about some of the theorems from section 1.2. So we have this definition of a vector space. We've looked at a few examples, and now we'd like to investigate some properties that all vector spaces have that will be convenient to be able to use over the course of the semester. Okay, so we'll start with theorem 1.1. Let's read this together. This is called the cancellation law for vector addition, and it tells us that if x, y, and z are elements of a vector space V, and we know that x plus z is equal to y plus z, then it has to be true that x equals y. Okay, so it's basically saying that you can cancel the z's on both sides of the equation. Okay, and you might look at that and think, well, you know, that seems pretty obvious. Why do we need to state that as a theorem and prove it? It really just seems like basic arithmetic. And I would agree with that if we were talking about real numbers here. We do know that if this were an equation that involves real numbers, we could just subtract z from both sides and we're done. But remember, we are talking about an arbitrary vector space here. X, y, and z are vectors, and that means that they could be very abstract objects. Maybe they're functions, maybe they're matrices, maybe they're tuples, or maybe they're examples of things that we don't even know about. Okay, and so to really prove this for all of those situations, we need to write a proof that uses only our definition of how we defined a vector space. Okay, so that's what we're going to strive for as we write this proof here. Right, so let's clear a little clutter away here. Okay, so we'll start by just taking some arbitrary vectors in our space. Take any x, y, and z in V. And notice that this is an if-then statement that we're proving, so we want to start by assuming the if part. Okay, so we'll be assuming that x plus z is equal to y plus z. And we're going to see if, as a result of that assumption, we can work our way towards x equals y, okay, using only the definition of what we mean by a vector space. Okay, so it's not as simple as just subtracting z from both sides, but one thing we know in a vector space, if you look at our list of properties, is that every vector has a negative. So the z that you see has to have a negative z. There's got to be a negative z in our vector space. So we could start by just adding negative z to both sides. Okay, that's valid because VS4 guarantees that the vector z has to have a negative. Okay, so we'll say it this way: guarantees existence of negative z. So it makes sense to introduce that vector into our equation. Okay, then next we'll do a little grouping. Okay, what vector space property allows us to do that? Okay, you can look back and maybe notice that that's VS2, the associativity property. That was part of our definition of a vector space. Okay, and then z plus negative z is equal to the zero vector. That's just the definition of what we mean by the negative of a vector. Okay, and recall I'm going to use the notation 0v for zero vector. Okay, so definition of the negative of z. And then finally, what happens when you take x plus the zero vector? You just get x. And that's by the definition of the zero vector. Okay, or we could say also VS3. All right, so notice what we did. We started with x plus y equals y plus z. We assumed that, and we demonstrated that that implies that x is equal to y using only properties of our vector space definition, and we are done. We have just proved this theorem.